Okay, I'm gonna say this again because I'm saying it so well, I just have to record it for posterity. And for the benefit of all my groupies around the world, okay? Seriously. Most people recognize the word proportionality. You've probably done it with the ratio of this is equal to the ratio of that. It's done with functions in this course, and it's going to be one of the easiest assignments in the course. I think. I just assigned it to the support course. Okay. And you're going to have very similar assignments. So just something to look forward to. Also to put some of the stuff that we're doing into some sort of perspective. Y equals kx is called a linear proportionality. It's got a straight line graph. Slope of k and y-intercept is 0. Okay, so it's straight through the origin. The slope is whatever k is. Very easy to apply. Now there's a procedure for applying it. I'm not going to talk about that. And if the camera would move, I'd be able to see for sure. I've got everything I think I have on here, and I don't. There it is. Along with my picture, there's a camera. Sometimes it gets bright and goes out of focus. Okay. What would you call y equals kx squared? Well, x squared is one of your favorite things because we've done a whole lot with the x squared graph and transformations of the x squared graph, right? There's no transformation involved, just a simple y equals x squared. It's a little blurred because I had some boards here when I was cleaning them. It's what you call a proportionality to the square of x. Y equals x cubed. And we just constructed the graph of the cubing function last time, is proportional to the cube of x. Y equals k squared of x is proportional to the square root of x. Okay, now what do you see here? You see the toolkit reciprocal function and the toolkit reciprocal square function. Here you see the square root function, which we constructed last time by inverting the columns of the squaring function. Okay, so something you're beginning to become familiar with. You have the reciprocal function. So you say it's inversely proportional to x. Okay, the reciprocal is an inverse proportion. Inverse proportion means as x gets bigger, y gets smaller. In all of these cases, if x gets bigger, y gets bigger. Like, what's the graph of x squared look like? Now, we're only talking about positive values of x. As y gets bigger, x gets bigger. What about x cubed? We just constructed that. As y gets bigger, x gets bigger, and it gets bigger faster than x squared. Something you should understand if you reviewed what we did in class last time. K times the square root of x is proportional to the square root of x. You know the square root of x has a graph that does this. Now, y still gets bigger as x gets bigger, but whereas the squaring and cubing functions get bigger faster and faster, this one gets bigger slower and slower. It keeps getting bigger, and there's no limit how big it can get. The reciprocal function, what's the graph of that look like? If x is positive, the graph looks like this. You know how to construct that graph. Everybody's very familiar with that graph. So there it is. The reciprocal square graph for positive x, it looks a lot like the reciprocal graph, but it's steeper and then it falls toward the x-axis faster. And the reciprocal square root, well, we haven't constructed that one. We're not going to worry too much about it, but later on you'll see how that can work, okay? Square root of x keeps getting bigger, so y keeps getting smaller as x gets bigger. Make sense? Halfway? You have something to relate it to. All the graphs we've been constructing and talking about up to this point will give you some insight into these things. And when you get to that assignment, you're going to see how proportionality works for real world applications, okay? Because that's really ultimately what we're after. Right now we're constructing graphs and learning the algebra. We're going to be moving into applications. I wanted to do that, but I didn't want to push too hard. Okay, pushing as hard as I think you can stand. So anyhow, that's where we're at. And kind of store that away and understand that the stuff we're doing keeps coming back. Okay, it never goes away. And you can model a whole lot of the real world with the functions that we're studying here and their transformations. one of the biggest things I saw on the tests he did, there were problems that said, okay, the h of x function on that test was the exponential, base toolkit exponential function. So, sketch a graph of the basic toolkit exponential function. Everybody did. Everybody had a nice graph. And I'll move this graph to the point 614 or something, okay? So they go to the point 614, they draw the rectangle, they draw the parabola. It's not h of x. It's not the exponential function. You're used to drawing the parabola, so you did what you're in the habit of it, which is great. You know how to do it. But that's not what the problem was asking you to do, was it? You have to draw the exponential function and then make estimates, write out what you think the formula is for that function, and compare your estimates with that formula. And if you compare it with the formula for the parabola, your estimates are not going to match up worth a darn. Okay? Does that make sense? So yeah, that's a matter of reading and understanding what you're asked to do. It didn't say draw the toolkit squaring function over here. That has nothing to do with the exponential function that we're looking at, or the reciprocal function. Okay? So make sure you do that exercise correctly, because I almost guarantee you that it's going to be on the test for one of those functions. Okay? Also on the test, be able to construct cubing function and the reciprocal square function. Okay? We did that in class last time. Know what the rules are. Make sure you know how to follow the rules. Okay? When I ask you to construct the three functions that we started with, I expect they'll be perfect. We do that, there are going to be three problems on there. Do the squaring function, do the exponential function, do the reciprocal function. And it's zero if they're not perfect. Now you have imperfections, cutting things in half. I'm not going to measure the lines you use to do the construction, but they got to be about right. If they're all equally spaced and this one has to be half of this one and this one has to be half of this one, it's not perfect. Okay? If they're plausibly cut in half, even if you're not particularly accurate on it, okay. Understand what I mean? And all the points have to be done according to the rules. No anomalous points. Now, I could put it all in one problem, giving you an opportunity to make zero on the problem because of one little error on one of them. No. But it's zero on a problem if you make one little error on each one. Okay? So it's going to be three problems, each worth 10 points, and an easy 30 points on the test. Okay? But it's got to be right. So I'm giving you a lot of points for something you should be able to do easily, for something that I almost always see done correctly. Okay? Test yourself on that. Make sure you know how to construct those accurately. Okay, so I'm going to ask you to construct one right now. And we'll go ahead with the squaring function, since that's the one you're most familiar with. But you should be able to do this by, say, the exponential function or the reciprocal function. Okay? But you ought to be able to make a good attempt at it by, say, cubing or reciprocal square. But it's only been 2 days. I'll give you a little time to make sure you sort that one out. Okay, so basic toolkit squaring function graph. Estimate and when I say draw the graph, I mean draw a big one so you can make reasonable estimates, okay? Make the biggest graph you can make on a page. It doesn't take any long. Your arm might get a little tired because you've got to draw longer lines, but you can handle it, you're young, okay? So estimate y if x equals 2.4 and x if y equals 2.8 and x is greater than 0. Subject to constraint x is greater than 0 because there are 2 points for y equals 2.8. Okay. So start with that, and then let me look at a couple of your homework assignments. I'm going to start on this side of the page. Class, you guys are on a page. Okay. Okay. So you construct your basic toolkit scoring function graph. You do a pretty big one. I always say the biggest one you can get on your page. And you do the usual subdivisions. And sometimes I see these lines almost equally spaced. Now, if you do the exponential function, they will be because you're not doing this line. Okay. But don't make that mistake. But if you were to measure my lines, it's pretty clear that they're getting closer together, roughly twice as close together. I look for that, like on the test. When I'm asking for a perfectly done draft, I want to see a plausible set of lines. And then we just, put our points in. I'm not gonna take the time and my red chalk and make the red dot. Actually, it's right here for you. And from there it is, we make an estimate. Okay. If x equals 2.4, okay. X equals 2 isn't even on the graph. So you wouldn't be able to do that, but I'm sure you can easily do 1.4. Okay. That's probably what you were asking. Yeah. I did show you how to extend the graph. Okay. We go twice this far from the x-axis, from the y-axis, and this is the y-axis. If it's the toolkit scoring function. We go twice this far, we go 4 times this high. So you could still extend it and make an estimate, but I'm not going to ask you to do that in the test or right now. Okay. But later on, I will expect to be able to extend it. I just showed you that last time. So, okay. So we'll do 1.4. Here's 1. Here'd be 1.5. So here's approximately x equals. Well, that worked out. Okay. X equals 1.4. And it looks like we got something just a little bit under y equals 2, right? Okay. And the intersection is at y approximately equals 1.93. Okay. I just say 1.9, the 3 is kind of spurious. Okay, pretty close to 2. It turns out that the actual square of 1.4 is 1.96. My graphs usually don't end up that accurate, so I kind of lucked out there. Okay, well, anyhow, then y equals 2.8. Well, here's y equals 2, and here would be y equals 3, so 2.8 would be maybe here. And so we want this point. And this point. Okay. So now what I want you to do is tell me what the average rate of change of y with respect to x is between those 2 points. How many of you know definition of an average rate of change? Taking what we have here, no reference to this. This is a definition that applies all the time, everywhere, universally. Okay? This is your definition. We'll apply the definition to this thing after we write down the definition, because changing that over changing this doesn't seem to necessarily apply to this case. Okay? It does, but we have to see the connection. So tell me, what is, we'll discuss this for a minute. Okay, so this is a little bit challenging for people because you probably haven't had much experience in relating two phrases and saying what the difference is. Okay, so you have an excuse. A couple of people did get it. So just look at this, average rate of change of that with respect to this, average rate of change of y with respect to x. What's the difference? Well, somebody said, well, y and x. Okay. And I said, well, what corresponds to y and x in this statement? Said this and that. That's wrong order, but that's right. Okay. So then I said, well, what does that correspond to? And everybody said, well, that's y, right? This is the average change of that average rate of change of y. And it's rate of change, not change. Rate of change, all three words. Okay? And I see that a lot. People just want to abbreviate that to change, and it totally changes the meaning if you don't have the rate word in there. So and it confuses your understanding. Okay? So you want to be really specific and exact about your terminology. Okay? Again, it's average rate of change of y, average rate of change of that. So this is y. So that corresponds to y. And this corresponds to, well, everybody said it's x. And where's my orange chalk? I need a different color. Okay. Okay, so whatever words replace that and this determine what you're going to do for the average rate of change. The average rate is then okay, change in y over change in x. That, y. Blue chalk. Oh, here it is. This, x. Okay. Do we understand how we can apply these words to get the definition? What about the average rate of change of z with respect to t? Could you write that one out? Yeah, it's change in z divided by change in t. It's a big deal. As I said, this is the whole foundation for half of calculus. Okay. Okay. So now, can you tell me? Okay, this boils my question here. Find the average rate of change of y with respect to x between these points, to finding the change in y and finding the change in x, right? So what do you think the change in x would be? Actually, I never made an estimate for y equals 2.8, right? So you could make that estimate. I'll make my own. This is like 1.5. So I'm going to say this is 1.7. Okay, so this line is x equals 1.4. This line is x equals 1.7. And I probably should have done those in a slightly different color so they don't confuse them. with our construction lines. Okay. So now tell me, what's the change in X? It's going to be a decimal. So you're going to think it's 0.10 or 0.9, you go 0.9. Okay. What do you think the change in X is? Okay, well, the change in X, what? At this point, X is 1.4. At this point, X is 1.7. If you believe my estimate, and I don't even believe, but something like that, okay? It's what it looks like on this graph. And actually, it turns out it's pretty good. Pretty close, okay? But that's just because my hand didn't work as it usually does, and I made a good graph. Okay. How much does Y change? Well, how much change is it? How much does X change if it starts at 1.4 and ends at 1.7? Yeah, that's why. X changes by 0.3, right? From 1.4 to 1.7 is 0.3. So now I'm going to use a little bit of notation here. I think most of you have probably seen the delta, the change. So how many? Is that familiar to pretty much everybody? Yeah, maybe not. Looks like about half and half. Maybe some of you just too tired to raise your hand. I can't blame you. Okay. Delta Y over delta X, right? So I'm going to write delta X instead of change in X. So over here, I can write out my calculation. I can write out delta X is 1.7 minus 1.4 equals 0.3, right? And you note that I take the later value and subtract the earlier value. Okay, we think of starting and going from left to right. Okay, now as I go from left to right, how much does Y change? Yeah, yes, it changes from what to what? Changes from 1.9 to 2.8. So the change in Y 2.8 minus 1.9. So what's the average rate of change? Write it down. Do the calculation. I haven't completed the calculation of delta Y, but it's 0.9, right? Okay. Well, people did pretty well. I only looked at a few papers, but everybody had it. So you want to write out, though, the entire Now, if all you wrote down was 0.9 over 0.3, that's fine for here. But when you write it out for yourself, you want to reinforce that the average rate is delta Y over delta X, and that's 0.9 over 0.3. Okay. And also, when you or anybody else reads what you've written, they'll know what you mean by 0.9 over 0.3. They won't have to go back and calculate everything. That includes you if you're trying to review for a test, right? And that's the most important thing if you're taking notes. Write out what things are and what they mean. If you don't have time to write it all out, because a lot of classes go too fast for you to do that, leave out what you think you're going to be able to fill in later and write the essential stuff and leave yourself space to write out what else you need to write. Okay. Just good advice. Of course, if you divide that, that's free. Okay. Well, I can, there we go. I can do this now. As I move from this point to this point, this arrow represents my change in x. And from here to here. But what I've got now is a path from the first point, the leftmost point, to the rightmost, indicated by these two arrows. Okay, and there's a different path I could, well, I could go up and then over, it doesn't matter. Okay, how far I go over is 0.3, whether I do it this way or this way. So this is 0.3. It's 0.3 and this is 0.9. There it is in a picture of your graph. Now you can also make estimates. Okay. And it's something I'll probably ask you to do for a quiz next time. And probably not for the squaring graph. I want you to be able to think equally well with the reciprocal or exponential. Okay. If I draw a bigger picture of this triangle, and actually I haven't completed the triangle. Okay, the triangle will go in a straight line from here to here. And an important idea, you can see that the straight line remains very close to the curve if the points are close together. Okay, if the points aren't close together, if I use this point and this point, the line would be here and it wouldn't stay very close to the curve. But the smaller the interval, the closer the more the curve becomes a line. That very important idea. So I hope you store that away for calculus. It should be pretty obvious. It's an important idea when you take calculus. It's going to be a year before you do that, but still. Okay, actually maybe just a semester, depending on the curriculum. So the average rate of change if it says from 1.4, 1.9 to 1.7, 2.8, the average rate of change is 0.9 over 0.3 equals 3. Okay. Now I'll mention there's this thing called the instantaneous rate of change. If you keep making these triangles smaller and smaller and smaller, still including this point, but bringing this point along the curve closer and closer, the slope doesn't, the slope of this line doesn't change very much. Okay. The slope of this line actually then approaches a limiting value of 2.8. So if you had a very tiny triangle, including this point, the slope would be very close to 2.8. And the slope here would be 3.4. Okay, 3 lies between 2.8 and 3.4. So it, again, watch out, lightning might strike or something, but I actually made some combination of an accurate graph and accurate estimates, okay? I knew what the numbers would be, but I didn't use those. I just made an honest estimate from my graph. Usually if we make an estimate from our graphs, they won't turn out to be this accurate. And really, a better estimate for the average rate of change would be 3.1. No, wait, 2 point. Yeah, 3.1. Okay. Very close. Okay. There's a correspondence between an important characteristic of a graph in what we've done here. Okay, I made a statement, say 0.9 is the rise. Does that make sense? If we go from this point to this point, we rise 0.9 units. And we call this the run, 0.3. So 0.9 over 0.3 can also be interpreted as the rise over the run on this graph, between 2 points in the graph. Okay. Now, how many of you know another word for rise divided by run? Okay, well, rise divided by run is slope. Slope of this line segment is 3. Okay. Now, if all you were told about slope is it's y2 minus y1 over x2 minus x1, it's probably because that's the way the book and the curriculum were set up. I don't think that's a good way to do it. I think you need to see it on a graph and understand first that slope is rise divided by run. Okay. And then apply the equation. Okay. And that would be y2 minus y1 over x2 minus x1. We can make that connection. You could also make it the other way, though. You could say, if you want to do it by a formula, okay, it's y2 minus y1 over x2 minus x1. There's your definition. And look, that's the rise divided by the run. You want to have both the formula and the idea of rise and run in order to understand the things you need to understand to go beyond an introductory first semester pre-calculus course. Okay. And you should have come to this class with that stuff ideally. If not, well, fix it right now. Okay. It's not difficult. All right. That's all I'm going to say about average rate of change, but I've said quite a lot, and your homework will tell you more and give you a lot of examples. Then a little later, we'll look at how we interpret these things, because that's really why we do this in the first place, because it has meaning in the real world. Okay. Like if the rise is how much money you make, and the run is how long it took you to make it. Like if you make $150 in 5 hours, if you got money versus time, you got a rise of $150. You got to run the 5 hours. So you divide that, you get $150 divided by 5 hours, which is $30 per hour. Okay. And if you're making financial decisions and stuff, this whole concept and the whole concept of an exponential graph, especially, and a variable graph become really useful. So just one example. All right. Okay, that's kind of a badly drawn picture that I'm constructing. You should be able to look at this and tell me what graph I'm constructing. Everybody knows. And that was very good. I'm always happy to see that. But right here, we got the reciprocal graph. Okay. This is okay. Well, I write this with a comma here. The comma got mixed up with my parentheses. This is y equals 1 over x, but I'm putting a little more information on it. I'm saying -2 is less than or equal to x is less than or equal to -1/2, and 1/2 is less than or equal to x is less than or equal to 2. Okay. Now, why did I say that? Well, what are my x values for the points in this graph? Let's just take a bunch of points in the graph, starting at the left. Here's a bunch of points, right? How do we get their x values? We draw projection lines to the x-axis. Okay. So now we see that the x values represented by points on the graph go from here to here and from here to here. Well, this interval starts at -2 and ends at what? -1/2, right? So let's just make sure we see, okay, this line here is x equals -2. This line here is x equals -1/2. And then this line here is x equals 1/2. And this line here is x equals 2. Now we have points from -2 to from x equals -2 to -1/2, but we don't have any between -1/2 and 1/2. If we extend this graph by continuing to go twice as close and twice as high as I showed you last time, we can go all the way up to 0, but we can't go to 0. And we can't be at 0, because no matter how many times we go twice as close, we never get there. We get as close as we want, but we never get there. That's a very important idea when you get to calculus, and it'll help you if you understand it now. To some extent, to the extent you understand it now, calculus is going to be a little easier for you. Okay. Now what about the y values? Okay, well, we say the domain is the interval from -2 to -1/2. And this U is the union, like a set union. In other words, you're in a set if you're in this part or in this part. And I hope that everybody's seen that. Usually everybody says they have. So I think that's pretty much standard part of the curriculum. If you don't understand it, well, Matt will explain it to you. And you can always ask next time, I'll explain it a little more. Okay. We call that the domain. It's all the set of x values. Range is a set of y values. Well, without going into much detail, if I take points in this graph and move over to here, I get this interval. And this interval. Now to complete it, I'm going to put a big old solid dot down here and a big old solid dot up here to show that 1/2 and 2 are included, so I can use the square brackets. Okay. And this is something that people generally understand pretty well and don't have too much trouble understanding if they didn't understand it at first. But you do want to be sure that you understand these dots and what we use closed brackets when you use open brackets. Okay. And if you look at the intervals, you got the union of two intervals that turn out to be the same as the intervals for the domain. Okay, well, there are more examples I could do, but I think if you understand that much, now there's some algebra involved, And we'll see how much trouble people have with the algebra. So we'll probably talk about the algebra a little bit next time. Okay. But the algebra is actually fairly simple. Just mostly algebra 1. Okay. Doesn't mean everybody's going to remember it though. So if you have a question on the algebra, email me. I'm glad to answer. Okay, brief synopsis. I think everybody will understand this picture, even if you didn't use it when you were supposed to on some of the problems, okay? So if I put my red dot here and make this my x-axis and make this my y-axis and sketch, I don't know, I'm either going to sketch the exponential or the reciprocal function. No, I'm not. I lied. I'm not going to do that. I'm going to sketch the reciprocal square function. Okay. And I'm going to call that function I'm going to have to come up with a good letter here. I'm going to call it y equals q of x. Now I want to come over to, I don't know, which square should I use? I'll tell you what. I'll come back here. My shoulder's not loose, so I might miss the board completely. But without looking, I'm going to try to hit that square on the board, and I don't even remember where it is. So there we go. Ah, came up a little low. Okay. Well, I'm going to go somewhere in this vertical line. Okay, I'm going to go to square somewhere in this vertical line. I'll try again. Shoulder stuck a little bit. That's my excuse. Okay, and my horizontal line, I think, comes here. So I'm going to go to this. Okay, those lines are in this square here. So I'm going to, I normally do the whole construction with all the lines, but we got 5 minutes left, so I'm not going to do that. And I'm going to sketch the reciprocal square function here. Okay. Now, we know that the dimensions in this grid, everything is supposed to be a square 4 by 4. So this is 0, right? So here's 4, 10, 12. And here, 4, 6, 4, 8, 12. Actually, you made me go to the point 12, 12, the way you held up my shoulder and stuff. Okay. Y'all caused that. Yeah, there it is. Now, what's the, okay, q of x. What's the formula for q of x? It's 1 over x squared. Okay. Now, if you understand the rule, this point is 12, 12. And this function is it's unfortunate we have the same number here, but you know how to do this. This is q of x minus 12 plus 12. That's something I think most of you are pretty familiar with. If not, you really need to go back and review videos and whatever it takes, because everybody should know that and should have known it for at least the past 10 days. Okay? Probably 2 weeks, maybe more than that. So if you're not there, get there, because you're going to need it in the test. Now, what's q of x minus 12? here's the way you would do well to write it out. Write out the definition of Q of X, and then directly below Q of X, write Q of X minus 12. So you know that X is being replaced by X minus 12. If you write Q of X over here and Q of X minus 12 upside down over here, you're not going to see the connection. And seeing the connection helps you build the connection. Okay, well, Q of X minus 12, you replace X by X minus 12, so it should be obvious that X is going to be, instead of 1 over X squared, 1 over X minus 12 squared. So Q of X minus 12 plus 12, well, is this. That should be obvious. If you have this lined up with the equal signs lined up, you can immediately see on your paper the connections and how you build up the formula for this function. Well, let's estimate the coordinates of a point. I'm not going to try to throw a piece of chalk and hit that unless I'm looking. In which case I'll hit the exact point I'm aiming at. Right. Okay. So I'm going to try to estimate this for X equals 13.1. So let's say here's 12, here's 14. Let's say that here is 13.1. Now you should be able to do this. If I say estimate this thing for X equals 13.1, you should be able to do it. Okay. Now then, here's the point where X equals 13.1. And what's Y? Let's see. If I cut this thing in half, it would be here. If I cut that in half, it looks like it's pretty close to 1. Well, not 1, but 1 unit higher than this, right? Looks like it's pretty close to 13. If I plug in 13.1 for X and evaluate this, it should come out pretty close to 13. And it does. I'm adding to 12. This is not what X is close to 12. It's 13.1. This would be 1.1 squared. Now that'll be a little less than 1. It'll be like 0.8. So you're going to get something like 12.8. Well, that's close to 13. My estimate is consistent. And if you understand that when you're looking at it right now and understand everything I've told you, you're in pretty good shape. If you don't, you probably ought to go back and look at it a bunch more times. But build it up by doing all the assignments, making sure you've got them all as perfect as you can get them. Okay? Because I think y'all are doing quite well. You probably should have started the assignment for last weekend a little earlier, and you should probably start preparing for this test as soon as you possibly can. All right.